Differential and integral operations 3, we're performing the line integral, closed path integral, dr cross v, where c is the contour that's defined by the square, x between minus 1, 1, and y between minus 1 and 1. And this time we're doing part b for the vector v0 ez hat. And on segment 1, remember, we have dy ey hat. We're going from minus 1 to plus 1, and here x is fixed at 1. So let's note that on segment 1, our dr vector, the small displacement vector here, differential displacement, is dy ey hat, and y changes from minus 1 to plus 1, and x is fixed at plus 1. And therefore we have dr1 cross product with our vector b equal to dy ey hat cross product with our vector v, which is v0 ez hat this time. Now, what is ey hat cross ez hat? Ex cross ey is ez, ey cross ez is ex. So following these cyclic permutations. So the answer for this is v0 dy ex hat. Now we can write our integral on the first segment, dr cross product with vector v. This is integral from y equals minus 1 to plus 1, v0 dy ex hat, and this will give us, the integral will give us a y, which is ranging from minus 1 to plus 1, so it is 2 v0 ex hat. All right, now we're moving on to segment 3. Segment 3, we have again dy ey hat, but y goes from plus 1 to minus 1, x is fixed at minus 1. So on segment 3, our dr vector is once again dy ey hat. Y goes from plus 1 to minus 1 this time, and x is fixed at minus 1. So dr3 cross product with our vector v is dy ey hat cross product with v0 ez hat, and once again ey hat cross ez hat is ex hat, so this is v0 dy ex hat, and therefore we can write the integral on the third segment to be, for dr cross v, equals to minus the integral on the first segment, dr cross v. So it's basically the same thing, but in the opposite direction. So the integral over the first segment and integral over the third segment for dr cross v add up to 0. How about the second and the fourth segments? Second and the fourth segments, we have dx ex hat. Therefore, we can write for these segments, dr vector is equal to dx ex hat. And we have either y is fixed at 1 or y is fixed at minus 1. When y is fixed at 1, x ranges from 1 to minus 1, and when y is minus 1, x ranges from minus 1 to plus 1. So let's look at that. When y is 1, x goes from plus 1 to minus 1. When y is minus 1, minus 1 to plus 1. So that's what we see here. Now, dr2 cross with v is dx ex hat cross product with v0 ez hat. How about ex hat cross ez hat? Ez hat cross Ex hat is Ey hat. So Ex hat cross Ez hat is minus Ey hat in the negative direction. So this will give us a B0 dx in minus Ey hat direction. All right. So the integral from plus 1 to minus 1, B0 dx minus Ey hat. And then we have the integral from minus 1 to plus 1 for the, because dr2 is equal to dr3. So this is true both for 2 and 4, the two segments. So V0 dx minus Ey hat. Once again, this is 0. So we find that the closed path integral dr cross V is equal to 0 once again, because 2 and 4 give us the same thing, 0, and 1 and 3 also gave us 0. Therefore, the total is going to be 0. So for this part, in part B, we have changed from B0 Ex hat to B0 Ez hat. In part A, we found that for segments 2 and 4, the answer was 0 because we had the cross product of Ex hat with Ex hat. So that problem was resolved in part B. We have cross product of Ex hat with Ez hat. But because the directions are reversed and we don't have any y dependence for this vector, there is no y in the components, we find that this also has to be 0. So we use dy Ey hat and dx Ex hat, and for each segment we consider minus 1 to plus 1 and x is fixed, or plus 1 to minus 1, x is fixed. And as for the segments 2 and 4, y is fixed at 1 and minus 1, x goes from 1 to minus 1, and then minus 1 to 1, because we have exactly the same form of the dr vector, and these are in opposite directions. They cancel out. Likewise, also in 1 and 3. Therefore, the final answer for the closed path integral is once again 0.